Let me introduce, I'm pleased to introduce Lara Bossinger, who's going to speak to us about Gröbner theory of Grassmannian cluster algebras. Lara.
Thank you so much, Nathan, and I would like to thank the organizers and the whole staff of the Isaac Newton Institute. This has been a very good hybrid workshop, like so far the best I have attended. And I'm going to talk to you about, as Nathan mentioned, the Gröbner theory of Grassmannian cluster algebras. And this talk is extremely close to what James has told us on Monday. So I'm really glad to speak at the same event as him to discover this close connection. So the motivation is the following. For me, Gröbner theory and cluster algebras are two subjects I really like. And in this project that's joint work with Fatemeh, Mohammadi, and Alfredo, we kind of got to really work at the intersection. But there's like a key distinction between cluster algebras and Gröbner theory, and that is essentially that Gröbner theory relies on some ideal. So to study Gröbner theory, I need an ideal in a polynomial ring for this talk. But cluster algebras, well, they don't really come to our hands in this precise form. However, we have the following theorem that you can find in the preprint of a book, Introduction to Cluster Algebras, that's on the archive by Fomin, Williams, and Selewinsky. So if we have a cluster algebra of finite type, A, and say XA is the set of all its cluster variables, mutable and frozen, then there's an ideal inside the polynomial ring of all these variables that represents the cluster algebra. And this theorem also tells us how to compute this ideal. The only thing we have to do is collect all the exchange relations and then saturate that ideal. So saturation, for people not familiar with it, this ideal, the saturation contains all the polynomials that if I multiply them by a monomial in all my variables, it will be contained actually in the ideal generated by exchange relations. So it's a bit more than exchange relations. So great, so this is kind of our entry to Gröbner theory if we're dealing with a finite type cluster algebra. And for most of the talk, I will be concerned only with finite type cluster algebras, namely those of Grassmannians. So the Grassmannian cluster algebra is the homogeneous coordinate ring of the Grassmannian under its Plücker embedding. So we've seen this algebra in the last talk. So embed the Grassmannian into the projective space of dimension n choose k minus 1, and a vector space in the Grassmannian represented by a matrix whose rows correspond to basis elements expressed in a standard basis of c to the n, where that one I will map it to this tuple of minors that are the Plücker coordinates. So in 2006, Scott wrote a very nice paper about Grassmannian cluster algebras and showed that exactly this ring, AKN, the Plücker algebra, is a cluster algebra. And moreover, it is of finite type in the following cases. So if the tuple Kn of integers is one of those, 2n, 3, 6, 3, 7, or 3, 8, well, including 4, 7, and 5, 8 that are isomorphic to 3, 7, and 3, 8. So then we can apply the theorem from the slide before and ask what's this ideal that represents the cluster algebra. And in the case of the Grassmannian 2n, this is a very nice ideal. It's simply the Plücker ideal. So in this case, the Plücker coordinates Pij, that are the coordinates on this projective space, are all the cluster variables. And the ideal representing the cluster algebra is exactly the Plücker ideal generated by these three-term relations that are exactly the exchange relations. So the middle term being the product of the exchangeable cluster variables. Now for the Grassmannian 3-6, the situation is slightly more complicated, but still very much handleable. So there are the Plücker coordinates that now have three indices, Pij, k, are still cluster variables. This will always be the case, but there's two more, x and y, that are quadratic binomials in Pij, k. And I think on Monday, in Anastasia's talk, these extra cluster variables also already appeared. So the ideal I36 contains the Plücker ideal, but as we're in a polynomial ring with two more variables than just the Plücker variables, it is different from the Plücker ideal, And this is just to give you an example. This is the minimal generating set. So this ideal is generated by all the degree 2 exchange relations. So those are the ones up here. And one more relation that kind of represents a photoimplicate relation, but including the variables x and y. Okay, so for most of the rest of the talk, I will be focusing exactly on these two cases, the Grassmannian cluster algebra for the Grassmannian 2n and for the Grassmannian 3.6. There's no real reason why I'm not talking about 3.7 and 3.8, rather than the results I'm going to present for the Grassmannian 3.6 are computational, and we simply did not do the computations for 3.7 and 3.8, but everything should work. That's the expectation. The same way for 3.7 and 3.8, and in a bit I will mention some further work that has been done. Okay, so then I'm going to start with a little background on Gröbner theory. Also, James has mentioned this in his talk. So what we're going to focus on now is the following setup. We're going to consider a homogeneous ideal inside some polynomial ring. This is the case for the two ideals that I've just introduced. And its Gröbner fan is going to be a complete fan in R to the n, whose fan structure is induced by taking initial ideals. So if I take two elements in R to the n, I will think of them as being weight vectors, putting weights on my variables in the polynomial ring, and taking the initial form of a polynomial is exactly forgetting about all the terms in this form that are not of minimal weight. And the initial ideal is then generated by all these initial forms. And there's a fan structure on R to the n that I can obtain by simply identifying weight vectors that give me the same initial ideal. So they by definition, or by a result of Mora-Robiano, R to the n has this fan structure. C circ here denotes the open cone C. And just a little notation. So having introduced this fan structure, I can talk about the initial ideal associated to a cone rather than just a weight, which is simply defined by taking any representative in the interior of the cone. And I will denote the quotient of the polynomial ring by the initial ideal by this AC. Okay, so now inside the Gröbner fan, there are two more interesting subfans. The first one is the tropicalization. Here I'm going to restrict my attention to all the weights such that this initial ideal does not contain any monomials. On the next slide, there's going to be an example just to kind of freshen up your memory on Gröbner theory. And if my ideal lies, only has a real coefficients, then I can also talk about the totally positive part inside the tropicalization. And that will be exactly all those weights inside the tropicalization, such that the initial ideal does not contain any non-trivial polynomial with only real positive coefficients. Okay, so these are the two subfans of the Gröbner fan that are interesting. I'm not quite sure if my citations here are correct, but there are certainly papers that will get you to more information. Okay, so let's do an example. Let's take the following ideal in a polynomial ring with three variables. All its coefficients are real, so we can talk about the positive part of the tropicalization as well. But first of all, by definition, the Gröbner fan now is R3, and it has the following fan structure. So if we now pick elements in R3, we will find, for example, this is the hyperplane where the third entry in R3 W3 is 0. We will find that there are three cones, three maximal full-dimensional cones. For example, if we go to this purple cone and pick a weight that lies in there, 1, 0, 0, and evaluate take this as a weight for the generator of the ideal, we will find that the first and second term get weight 2 and 4 respectively, and the last term gets weight 0. So the minimal term in this case is this third monomial, which corresponds to the initial ideal to all of this cone. The reason I have drawn only a two-dimensional picture is that homogeneous ideals always have what is called the linearity space. So if I pick a weight that lies in the span of this 1, 1, 1 vector, then the initial ideal will not be different from the original ideal. That's simply because 1, 1, 1 is exactly the grading that makes J homogeneous. So if I quotient out by that one-dimensional linear subspace, I get a two-dimensional Gröbner fan, and I can draw it, for example, in this hyperplane W3 equals 0. Okay, so now the tropicalization is the one skeleton of this picture. Namely, it corresponds to these three one-dimensional cones, these three rays, whose initial ideals are exactly binomials. And the monomials appearing in this binomial ideal are corresponding to the two monomials that are adjacent. So this is what James explained to us. If we have these, if we require two weights in a three-term relation to be the same, what we end up is exactly a phase of a maximal cone. And the positive part of the tropicalization is exactly the union of these two rays, or the subfan that has this pink ray and this green ray, because these ideals do not contain any non-trivial elements with only real positive coefficients. Okay, so in this context, I want to introduce one more definition, namely that of standard monomial basis, which is a very important and very powerful tool. So if I have a monomial ideal and take the quotient of the polynomial ring by the monomial ideal, the set of all the monomials that are not contained in this monomial ideal naturally gives me a basis for the quotient, a vector space basis. And the same is true if this monomial ideal is the initial ideal of my ideal I started with. So if A is the quotient, in this case of the polynomial ring of three variables by J, then for every maximal cone, I will get a standard monomial basis that consists exactly of the cosets of all the monomials that are not contained in the monomial ideal. Okay. Are there any questions on Gröbner theory? So feel free to interrupt. Okay, it doesn't seem to be the case. Then let me continue. So in this paper with Fatemeh and Alfredo, what we did was generalize slightly the standard construction of degenerations by initial ideals. So if you pick any weight inside the Gröbner cone, you can write down a flat family or deformation of the algebra A that degenerates it or deforms it to the quotient by the initial ideal. And the way to do that is simply by introducing one more parameter and homogenizing all the equations with respect to the weight vector. So we can do this for several points in the Gröbner fan at the same time. And a particular interesting case is picking a maximal cone in the Gröbner fan and doing this homogenization with respect to all its rays or representatives of the primitive ray generators in the quotient by the linearity space. So if R is the matrix whose rows are exactly these primitive ray generators, then first we define this minimum function that for a given polynomial has entries corresponding to the minimum of all the dot products of the rays with the exponent vectors that appear in the support of F. And then we can lift this element F, or kind of homogenize it with respect to all these rays at the same time by introducing one T parameter, one parameter for every ray, and simply instead of just evaluating F in the variables x1 to xn, we evaluate in these monomials of T's and times the variables x. To, in the end, get some terms that actually do not contain any T's, we multiply by this monomial whose exponent vector is minus this minimum vector. So what we get, if F was my polynomial whose with monomials x to the alpha, then what we obtain here is exactly that every term x to the alpha is multiplied by a monomial in t's, whose exponent vector is this R matrix times alpha minus the minimum vector. And the theorem that we showed is then first, this lifted ideal has a very particular generating set, or like several, whenever you have a Gröbner basis for the ideal J with respect to the cone C. So a Gröbner basis is a set of generators for the ideal whose initial forms also generate the initial ideal. Then the lifts of those Gröbner basis elements will generate the lifted ideal. And what we show is then that the lifted algebra, so that's this A tilde, I'm sorry, I think I forgot to put it down as notation, is the quotient of the polynomial ring in T's and X's by the lifted ideal. This is a free CT1TM module, and it has the same vector space basis as A, and that is exactly the standard monomial basis associated to the cone. Okay, so let's look at the example that was on a few slides before. This is our element F, and we consider this purple cone in the Gröbner fan, whose primitive ray generators are these 1, 4, 0 and 1, minus 2, 0. Then we can just do the construction as before. So here we plug in monomials in T's that correspond to the columns of my matrix. So x1 comes with T1, T2, x2 comes with T1 to the 4, T2 minus 2, and x3 does not have any T parameters at all. And the minimum vector, if you compute it, is minus 4 and 2. So if we evaluate, we get the following expression, the following polynomial in T's and X's. And now the key point of this construction is the following. If I now vary T1 and T2, so remember these, I think of them as deformation parameters. If I vary their values between 0 and 1, I kind of interpolate between the ideal, or in this case, just the polynomial f, and its initial forms that are associated with all kind of faces that appear in my cone. So for example, if I evaluate at 1 for the t's, I just get back f. If I evaluate both t's to 0, I'm left with simply the initial monomial corresponding to this maximal cone. And if I evaluate at 0, 1 or 1, 0 respectively, I get the initial form of the two rays. So in this case, the lifted algebra is simply the quotient by this, the quotient of the polynomial ring in t's and x's by this polynomial, this f tilde polynomial. Okay, so with all this set up, I can tell you about the applications to the Grassmannian cluster algebras. So now we're thinking of the algebra AKN, where KN is either 2n or 3, 6, one of the two cluster algebras of the Grassmannian. And in both, and IKN is the idea that we've seen in the examples before. So for 2n, we're looking at the Plücker ideal, and for 3, 6, we're looking at this cluster exchange ideal. And in both cases, in the Gröbner fan of this idea, we can find a unique maximal cone that has the following properties. First of all, I didn't mention, but this is a smooth cone, so it is simplicial, and its rays generate a lattice basis, or its rays are lattice basis. The first observation is that the initial ideal associated to this cone is generated by the product of all non-compatible cluster variables. So this is exactly the cluster adjacency condition that appeared in the talks on Monday. And in other words, this monomial ideal is the Stanley-Reisner ideal of the cluster complex. So these binomials, it's generated in degree 2 by these, monomials, are exactly the minimal non-faces of the cluster complex. Then secondly, we have a canonical isomorphism of the lifted algebra with the cluster algebra with universal coefficients in this case. So I did not introduce the cluster algebra with universal coefficients because I thought half of the audience probably knows it, and for the other half, introducing it in 2 minutes might be a bit tough. I encourage you to look at it. I think it's probably the coolest cluster algebra of a fixed given type that there is. The idea is that the universal coefficient algebra, or how I think about it, is exactly a way to endow a given cluster algebra of some fixed type with coefficients in such a way that by coefficient specialization, you can obtain any other cluster algebra of the same type. So if you like, it is a family of deformations of a cluster algebra of given type that interpolates between all the possible coefficients that you could choose. And this is Nathan's work that explained to us how to construct it, at least in finite type, in a very precise way. So this isomorphism that we wrote down sends the universal coefficient. So there's exactly one universal coefficient for every mutable cluster variable, and it is exactly in bijection, or it's a one-to-one correspondence with the rays of the cone C. Then the next point is that the cluster monomials that form a basis for the cluster algebra with universal coefficients coincide exactly with the standard monomial basis of this cone. This is essentially just a consequence of the first observation about the initial idea. And now we can also look at the tropicalization of these cluster ideas and their positive parts. So if you take this maximal cone C and you intersect it with the tropicalization of the idea, what you obtain is exactly the positive part of the tropicalization. So in particular, we get the following bijection. So the tropicalization in this case is a geometric realization of the cluster complex. This was shown already by Speyer and Williams, but in a very different way. So we get here bijections, or really one-to-one correspondence between the rays of the positive part and the cluster variables, and the maximal cones of the positive part of the tropicalization and the seeds of the cluster algebra. And lastly, there you can associate to every seed a valuation. I'm going to talk a bit about it on the next slide, and a toric variety that is a degeneration of the Grassmannian. And it turns out that if you pick a cone in the tropicalization, in the positive part of the tropicalization, and consider the corresponding projective spectrum of the Gröbner degeneration, then this coincides with the toric variety that you obtain from this, the G-vector valuation on the cluster algebra. So before I go into a bit more details on the last part, this is also kind of our chance to generalize for other Grassmannians. I want to mention that last week, I believe, there appeared a new paper on the archive that generalizes this work. So Nathan Ilton, Alfredo, and Hipólito Trefinger generalized point 1 of this theorem for arbitrary finite type graded cluster algebras, and points 2 and 3 are generalized to types ADE in their work. And if you're interested, I encourage you. I think Hipólito is active, like non-virtual participant of this conference. Okay, so then let me use, I think, the last probably 5 minutes of my talk to give you a bit of an explanation about this story of toric varieties and how it could help us to generalize for other Grassmannians. If I have a seed of my cluster algebra, and now we're talking about the Fluker algebra for arbitrary Grassmannian, then I can associate with it a full rank valuation that goes from the cluster algebra without 0 to some lattice z to the d, where d here should be the dimension of dimension plus 1, the dimension of the Grassmannian plus 1, the dimension of the affine cone. And what this evaluation does is for cluster monomials, it simply sends them to their G vector. So I take the principal coefficients at the seed S, and I map a cluster variable to its G vector. This extends to evaluation. So this was shown, for example, by Fujita and Oya in their paper that's, I think, still a preprint. And if I have this valuation, there are several ways how I can get to a toric degeneration of the Grassmannian. In this toric degeneration of the Grassmannian coincides, for example, with the degeneration of GHKK that they construct from the cluster variety with principal coefficients, or a compactification of it. So now there are some general results about relating toric degenerations of the Grassmannian that are induced by evaluations on the homogeneous coordinate ring, relating them to maxima cones in some tropicalization. So these are results by Cave and Manon, for example, or also in a paper of myself, where you can find theorems that, not too explicitly, but that give you this bridge. The idea is to consider the image of this valuation, that's by definition a semigroup, and then represent the algebra as a quotient of a polynomial ring where the polynomial generators are in bijection with generators of the image of the valuation. And then, well, by simply taking a kernel, so a map, write down this map from the polynomial ring to your algebra, and take the kernel, and that will give you a presentation. And the theorem says that in the tropicalization of this ideal, you will find some maximal cone whose initial ideal is a prime binomial ideal, so an ideal defining a toric variety that coincides with this toric variety that you found from the valuation. So here's a conjecture, I would say like 90% proved, but still not 100%. So I will formulate it carefully as a conjecture. If you do this now, so if you apply this theorem, this general theorem, I mean, it works more generally for just projective varieties and the homogeneous coordinate ring for some embedding of the projective variety. If you apply this general theorem to the case of the Grassmannian together with this G-vector valuations, what you will find is not only a maximal prime cone in the tropicalization, but actually a prime cone in the positive part of the tropicalization. So J here is exactly an appropriate ideal, giving us such a presentation. And moreover, if this ideal J is appropriate for two adjacent seeds that are related by cluster mutation, then the corresponding cones in the positive part of the tropicalization share a facet. And yeah, as a remark, so here what I said about J being appropriate, it's exactly the following. So if in this quotient the cosets of the generators of the polynomial ring, if the images of those cosets under the valuation generate the whole image of the valuation, then the ideal is appropriate. So just to finish, I wanted to kind of tell you in the examples of the Grassmannian 2n and 3.6 how this works. So for the Grassmannian 2n, the value semigroup of these G-vector valuations is generated by the G-vectors of all the Plückel coordinates. So this is simply because the Plückel coordinates are all cluster variables, so there's really no other choice here. And in this case, the Plückel ideal is appropriate for all seeds. For the Grassmannian 3.6, well, as we have these two cluster variables x and y, it's not such a big surprise that you can find some seeds such that the valuation or the G-vector of x and the G-vector of y do not lie in the semigroup generated by the G-vectors of Plückel coordinates. And this picture, I took it from the paper of Reach and Williams. These are two Plabic graphs that are that induce seeds that are exactly not appropriate in this sense. And these are the two where the flow valuation of Reach and Williams has a non-integral Newton-Cookov body. And lastly, conjecturally, the ideal IA representing a finite type cluster algebra A is expected, or I think it is appropriate for all seeds in the above sense. But then thinking about it, I realized that maybe one should be careful and just sit down and check this. So I said conjecturally, but I'm pretty sure this is true. Okay, thank you very much for your attention. I'm going to leave you with some references, and yeah, that's it.
Are there any questions for Lara? Let's start with questions in the room if there are any.
Hi, this is Matt. Can you just go back a couple of slides to when you defined the valuation?
Oh, yeah, I didn't really define it. But
yeah, so you said a bit how this was defined, then could you just say it again?
Yeah, so what you really need, okay, so the easiest way to get to this valuation is considering the theta basis of Grosecki, Kiel, and Kontsevich, because all the theta basis elements also have associated G vectors, and they're not necessarily cluster monomials. So you get already here like a map that sends every basis element of the cluster algebra to its G vector. And to turn this into a valuation, you need a total order on the lattice. And for that, you can use the dominance order, I think Van Kien's dominance order, and refine it to make it a total order. Any refinement will work. And then you can map any element of the algebra to the minimal G vector of the theta functions appearing in its like linear expression in the theta basis.
So D was the dimension of the cone on the Grassmannian?
Yes, so the number of mutable and frozen cluster elements.
So are these G vectors in the natural Grassmannian coefficients? You said principal coefficients, and I didn't understand why. The lattice seems to have the wrong rank for principal coefficients.
Ah, sorry, yes, okay, no, very good point. Thank you for the question. I am taking like extended G vectors. So if you want to get them like in a Fomin-Zelevinski way, you should think of all the frozen variables of being mutable and take G vectors in that kind of bigger ambient cluster algebra.
So then how do you get down to ZD from Z2D?
Wait, 2D?
If you put principal coefficients on, when the seeds have rank D, including the frozen. So if you put principal coefficients on everything, then you end up with 2D things, I thought. Or you're only taking the extended part.
I mean, the G vectors should have length. Well, classically, they should have length the number of mutable variables, right?
Yes.
Yes, and now I just add in frozens.
But not principal ones, just the frozens in the Grassmannian cluster algebra.
Yeah, just the frozens.
Okay,
Okay. I mean, yes, yeah. No,
okay,
I mean, I just had
yeah.
principal coefficients because I mean, you just need to put principal coefficients to compute the G vectors, right? That's all. Like, yeah. I'm sorry. No, it's
okay,
just
I
usually...
don't think so, but you can probably use principal coefficients to compute them. Okay,
yeah.
thank you.
Yeah. I'm sorry for the confusion.
That's fine.
Other questions?
If not, there's a question in the chat. Greg, would you like to voice the question? Should I repeat it for you?
Sure. Nice talk, Lara. I was wondering, are these all the possible valuations? Or are there examples of evaluations on AKN that would not come from GS for some seed S?
Yeah, very good question. Thank you. Yes, they are indeed. The way to think about it, I mean, this theorem here, you can really think about it as giving you, in some sense, a bijection. It's not on the nose a bijection, but if you fix some presentation fix the Plücker ideal, for example, and look at its tropicalization, then for every maximal cone in this tropicalization whose initial ideal is binomial and prime, you have a valuation that corresponds to that toric ideal that will give you the same toric degeneration. But the seeds, they will always give you some, well, they will always correspond to maximal cones in the positive part of the tropicalization. So for example, I think for the Grassmannian 2n, in the end, everything will be isomorphic. So it's kind of enough to look at these seed valuations. But for the Grassmannian 3.6 already, you can find some maximal cones in the tropicalization of the Plücker ideal that give you valuations that are not isomorphic to any of the seed valuations. So in general, yeah, the tropicalization is way bigger than the positive part. And there's even up to isomorphism, the positive part not necessarily recovers all the rest.
I see. So I don't know if this is well defined since it would be outside the positive part, but does that mean that you could take some other maximal cone that's not necessarily in the trop plus, but just trop, and reverse engineer a quote unquote G vector map that really isn't for a seed, but for some other structure?
So what you can definitely do that is by this paper of Kaviman, they tell you how to cook up evaluation on the Plöcker algebra in this case. So you get to this point. I have not thought about it if that would give you some kind of non-cluster cluster structure, but it's definitely very interesting to kind of start and like, yeah, think backwards. Now, given an evaluation, can you get something like a seed? I guess you can get a torus chart on the Grassmannian by just taking these the generated, it's called the Kowalski basis, like the algebra elements that generate the value semigroup. I think from the Kowalski basis, probably you can get a torus chart, but I have no idea if you can then kind of start gluing or something like that. That would be very interesting to study, actually.
Thank you, and thank you for the nice talk.
Thanks.
Let's thank our speaker again.